All right, let's try this recording again. Looks like it's working this time. Awesome. And so, okay, self-driving cars, they got all these sensors on them, and they have to be able to draw little boxes, right, around all the other cars. They have to notice where the lights are. The lights could be sideways in the U.S. in some places. They could be up normally in some places. You have to notice little, like, signs. You can kind of see that. Signs that say what's about to happen, like stop signs, of course. Notice pedestrians and not hit them. Maybe you need like infrared for that to notice the body heat or something. And then, of course, a very important thing is you have to notice the lines of the road too. Like, we cannot drive over here. We can drive over here. Yeah? So all these things have to be happening in the blink of an eye inside of a computer. So machine learning is getting powerful, and we're able to do that kind of computation very quickly. Pretend like we're humans. It's like our brains do this. Eventually, maybe a computer can do it quickly, right? So you have to figure out, like, where's the road? Where are the other cars? I don't want to hit them, even if, like, I can see the road. So, yeah, once you figure all that out, then you have to control the car, too. You have to, like, all right, let's move the steering wheel just this much. Let's press on the brakes just this much. Let's not slam on them, right? And so that's what you have to do to program a self-driving car, and that's why it's so hard. That's why they haven't really been, they don't really exist everywhere. So a cool thought that I heard on the internet that people keep saying is, like, in the future, we may not even need to own cars, because we can just have self-driving cars, so they're just driving around the road. We can just be like, all right, I want my car right now, and like one of the ones that was empty will just come in off the road, pick you up, and take you where you need to go, and then go take somebody else. So, like, we'll never need our own cars, potentially, once they become all self-driving. But that'll be a while, because there's still plenty of issues to iron out. So here's a fun one. Like, some people, they taped a bit of black tape on a speed limit 35 sign, and it convinced some Teslas to think, like, oh, that meant 85, and they, like, slammed on the accelerator. So that's a bit of a problem, right? Humans can notice, like, oh, okay, something's wrong here. This is a residential neighborhood. I probably shouldn't be going 85, whereas a computer would be like, oh, yeah, that's the number you want me to go. See the problems there? So it takes some thought, and that's why they're not ready yet, I would say. All right? Yeah. I agree, yeah, and this, just like, are they programmed? Yeah, and I assume the Teslas were programmed, their autopilot features were programmed on U.S. roads and U.S. road markings, and so maybe it gets confused even more in other countries. That's a great idea, a great thought, yeah. That's exactly right. So that's going to take a lot of work. We'll get there, though. So yeah, that's just some new ideas that are important that have to do with artificial intelligence. There's also social media. Artificial intelligence is being used all over the place. Machine learning is being used all over the place to, like, deal with mean people that post silly things that shouldn't be posted, right? So, like, you could imagine that you've seen on Reddit or on Twitter or whatever it's called these days that, like, people are just saying mean stuff, and things that are extra mean should probably not be posted, right? It should be, like, removed from the app, speech especially. So it's really hard. Like, you can't employ enough people that work at Twitter or that work at Instagram to, like, go through every single comment. There's just way too many of them being posted every second. Like, there's probably millions of tweets a second or more. And so you kind of have to automate this process to notice, like, all right, what's bad? What should we not allow to be submitted to our social media? And so some nice strides have been made in the natural language processing area of artificial intelligence that, like, analyzes. We have the ability now to analyze a sentence and notice, like, was this a happy sounding sentence? Was it a sad sounding sentence? Was a very angry sounding sentence? And the most angry of the sentences can be, like, fed to a human to look at. So that's kind of a triage process that we can do these days. That's called sentiment analysis. That's a topic of current research in artificial intelligence. You can figure out the tone of writing. So yeah, we'll be able to do that better and keep the internet a happier place, in theory, when that gets better. Yeah, one of the last few things I want to talk about is just, like, artificial intelligence getting so good that it kind of tricks us. Have we heard of the Turing test before? like, it's named after Alan Turing, very famous man in computer science. And the idea of the Turing test, I would claim that computers can pass the Turing test these days, but it used to be like a pie-in-the-sky dream. Like, can we make a computer that's so good and can think so well that will pass this thing? So here's the setup. Here's what the Turing test is. It's meant to prove like a computer is identical to a human, essentially. So here's the Turing test. It's like a game that you can play. And so here's the game. If you want to be, let's pretend that you are involved. You're taking the Turing test right now with a computer. So a researcher is going to take you. So you've signed up to do the Turing test. They're going to take you into a room, and they're going to give you a computer with like Discord open or something. So they're going to give you a laptop. So there's your computer. They put you, your person C, they put you into a room, and there's two people on that Discord server. There is a human, and there's a computer. Okay? And you can send messages. You can talk to each of them. You can talk to each of their usernames or whatever, and you can ask them questions. They'll reply with text answers. And at the end of the experiment, your job is to say who you thought the computer was. Does that make sense? That's the Turing test. And this used to be like a dream of artificial intelligence. Like, can we make a computer that can do this? That can trick a human? I would say that with the modern day advances of like ChatGPT and all that, you would get fooled. Like, if the computer fools you, if you're unable to tell like more than just chance, like 50-50, then we say that the computer passed the Turing test. It successfully tricked you into thinking it was a human. It essentially, for all intents and purposes, acted like a human. Isn't that wild? And so, yeah, depending on how long you can take that test, like if it's just a few minutes, you can talk to everybody. I would say modern day, like natural language or large language models can fool people pretty well, right? Talking to ChatGPT, if we've tried it before, like it sounds like a human responses, right? So yeah, that's a thing, and that's crazy, right? So I would say that computers can pass the Turing test these days, and this used to be just the dream of artificial intelligence researchers. It's finally, in the last few years, become reality, and so we're living in some very exciting times, I would say. Before ChatGPT came out, this slide like blew people's minds. It doesn't blow anybody's minds anymore, of course. So let me just like zoom in, like what I did back in the day, before ChatGPT was a thing and before artificial intelligence was very popular. I showed everybody like this text, and it's like some sort of example of a large language model generating text, right? And it seems like a normal news article, and I'd be like, do you believe that this article was made by a computer? And everybody went, oh, wow. Nowadays, it's like, all right, that's normal. That makes sense. ChatGPT is that good. But yeah, you just gave it like the idea of the GPT-4o or whatever the number is these days. Is it's a neural network. It's just a bunch of little artificial neurons, right, hooked together, sending numbers around that eventually correspond to text. Right? It's outputting text somehow into the virtual brain. And it's thinking. You give it a little prompt, it can understand what you asked it to say. Like you can say, write a fictional news article or something. And like I think it was GPT-4 or 3, I can't remember. It had 175 billion little virtual neurons sending virtual information, numbers essentially, around this virtual brain. Isn't that cool? And so, yeah, don't use it. Like, hopefully you've been yelled at by like English teachers. Please don't do this to write your essays or something. That would be a very bad idea, because then you don't know how to write anymore. It's a huge problem in the English field, I would say, these days. So yeah, that's GPT. It's a type of neural network, and they're just getting better and better. All right. So have we all used ChatGPT before?
For getting sources.
Yeah. It's helpful if you use it right, and to not cheat. So let's just like if you have a ChatGPT account, just go on there for a second. I want you to like just experience it again if you haven't in a while. There's also this website where you don't need an account, sdk.vercel.ai/prompt. Apparently, you can also give it a prompt there. That's that one. But you can log into ChatGPT if you'd like. Let's see here. Oh no, do they now want us to pay? Oh no, here it is down here. You can give it something. You can give it the, oh, you can ask even you can compare models. Here's the Facebook Llama model versus the GPT model. That's kind of cool. So here, you can give it like a sentence as a prompt and like ask it to do something cool for you. Tell it to convince you to become a computer science major or something. I don't know. But I think a good thing to do right now is just to get the cheating out of our system. Let's ask ChatGPT to write one of our old essays and see how good it was, how good it does, and then we'll never do it in class, okay? So I think that would be a good one, a good example. Let's have it write, I don't know, which one? We can do Therac 25, we can do, yeah, Therac 25 essay sounds good, right? That was the most recently due one. What was that essay about? So tell me what you would have done differently to prevent the disaster. So here, please write, ChatGPT, please write a short essay on the Therac 25 machine, or disaster. Is it? Oh man. Please write a short essay on the Therac 25 disaster and tell me what you would have done. Talk about the issues and tell me what you would have done to prevent the disaster if you were in charge. Well, I guess I can log in. Does the Llama model let you do it? Dret. There's other websites. You can, I think just, do you even need a ChatGPT account? Okay, cool. Here, ChatGPT. Please write a short essay. You just go to chatgpt.com. And so here it goes. Like, obviously, doesn't really look like an essay, but it's close enough. Like the Therac 25 disaster is a poignant example of the catastrophic consequences that can arise from a combination of software flaws. If I see you guys using such big words like this, I know that you use ChatGPT, by the way. So please, don't try to test me. Inadequate safety protocols and lack of effective communication developed in the 80s was a radiation therapy machine. Unfortunately, several incidents like caused an overdose, serious injuries, and in some cases, fatalities. Okay. It's talking about the issues, right? Relied heavily on software for safety features. And so here's what I would have done differently. I would have tested more. I would have brought the users who are going to use the machine in. Like, you see, it's giving you ideas and thoughts. Don't do this in this class or in your English class, because that's really bad and it's not going to teach you how to think for yourself. We want you to think for yourself. But you can use this to help you, right? To give you ideas about things or to find resources for you to learn more about the material. But you can see how good of a job it does these days. That's passing the Turing test for sure. Yeah. Any questions about that? Does that make sense? It's a fun idea, right? It's pretty cool. So we're never going to use this in the class now, but, unless we use it for a constructive purpose. All right. I think the last thing I want to talk about before I switch slides is to just scare you a little bit. Have we heard of a concept called the singularity? It's one of those weird ideas that the tinfoil hat people would say. It's a little funny, but maybe one day, honestly, it could be true. It could ring true. So here's the idea of what's called the singularity. It's like a bad thing that might happen if artificial intelligence got too powerful. So notice that we've made already really, really good machine learning models that can play chess or play Go better than any human, right? Because they're playing against each other and they're getting just faster and faster and better and better. They're training themselves against each other and getting better each time without a human taking over. They just know the rules and can figure out the right strategies. And so essentially the computers are thinking on their own. They're learning from each other and thinking on their own, right? So, and that's just for a specific task like chess or some other game. What would happen though, consider, right? What would happen if you did the same, we made a computer that was just smarter in every general way, like in engineering and in physics and any area of knowledge compared to a human? What if we made a computer that was smarter than a human, like a machine learning model, like ChatGPT, that was smarter than any human, okay, and could come up with research ideas, and we could follow it, we could do its bidding and carry out those ideas. That computer could function like a human and would be smarter than a human, right? Maybe one day we'll make a machine learning model that's smarter than any human. And imagine that, like, we make the first model or implement the first computer that has that hooked into it, right? That has more intelligence than a human. Well, then we could copy that thing, right? And make a bunch of smarter than human computers that could think better than we possibly could as humans, right? And then, here's the kicker, we could ask that smarter than human hive mind of computers, right, to invent a better version of itself that we would never think of because we're not as smart as it, yeah? We could ask it to do that, it's totally fine, and it will come up with a better version of itself that we never would have thought of, and we can go off, take its blueprints for that new version, build it, and then ask, like, make 100 of those, and ask that hive mind, very, very smart computers, even smarter than the last batch, and definitely smarter than us, to go and think of a better version of itself. And we can keep on iterating. You see that? And we can just make computers that are smarter and smarter and smarter, and that come up with better versions of themselves, and eventually we will have super intelligence. Like, we couldn't even, like, make a computer faster. Like, that is as fast as physics will allow. Like, one day we might have that, and that is called the singularity. Okay? Where computers just take over, essentially. So it's a little scary, I don't know. If we trust computers, maybe that's nice. If they're nice to us, I think this sounds like a good future. I don't know. But here's a fun quote. So this person said, the first ultra-intelligent machine is the last invention that man need ever make, right? Provided that the machine is docile enough to tell us how to keep it under control. So hopefully that ends up ringing true. But, like, every invention, every research idea, the second we make a computer smarter than us, like, it's going to do all the thinking. It's going to improve our lives, and we don't have to do anything, right? Essentially. So that's called the singularity. It's a wild little concept, but yeah, that's where I want to leave us on our artificial intelligence slides. A either hopeful or scary idea of the future. Okay. Any thoughts or comments about that as I open up the next set of slides? Yeah. A little weird to think about, I know. So there's that one. I want to talk about a more logic-y concept now. We'll get away from scary thoughts, bad ideas, things that computers are not doing well. Let's just go back to pure logic, nice math, safe math, right? What I'd like to do is start with a topic called qualifiers. That's more Englishy stuff. And we'll talk about something called quantifiers, which is an advanced logic concept, all right? So I want to talk about qualifiers first because they make more sense to us as humans. We use them all day long. So a qualifier is just like something you use as you're making an argument. We're going back to arguments now, right? Because, like, you don't want to make sweeping generalizations. You don't want to, like, nothing is ever absolute when you're arguing something. There's always special cases, right? And so, like, let's look at how we can soften our statements when we're making an argument so that they're not, like, claiming something that's not really true, okay? So here's an example of a sentence with a qualifier in it, all right? Almost every day is unbearably hot in Fresno when it's July, which is usually true, right? So somebody might come along and be like, you know what, you're wrong. If I said that, like, somebody might tell me, no, you're wrong. There was that one day when it was cloudy for some reason, and it was only in the 80s. So that was a very nice day. But my sentence is still correct, right? Because I said this. I said the word almost, didn't I? I said almost every day, and that's called a qualifier. I've qualified my statement. I didn't say every day. I said almost every day. See that? So it's still a true statement. That's called a qualifier. And so we use these all day long, right? So we're softening our statement, qualifier, because otherwise they might be incorrect, right? We use words like that all the time. And so here's just a list of qualifiers that you've gotten to know and love, right? So there's a whole spectrum of them, right? You can be very specific, you can be very precise, and sweeping if you want to. You'd be like, nothing is true about this thing. It's never hot in Fresno in October, which is definitely not true, right? Or every day in July is really hot. It's no fun, right? So, like, you could have those ends of the spectrum, and then there's everything in between, right? All right, there exists a day where it's not as hot. Almost no days are cool. Some of the days are cool once it starts becoming cold, right? Usually, it gets cooler by the time we hit November. Almost all the days in December are freezing, are very cold. In theory, right? And so, like, you got all these ideas, right? You have the ends of the spectrum, and Everything, all the gray areas in between. So those are qualifiers, all right? And it helps us be precise when we're trying to talk about things, especially when we're writing essays or we're doing research, like science, especially academia, especially. You can, like people are using qualifiers so that they're not making an incorrect statement. Right? Usually it's not the case. You shouldn't always say it's always true or it's never true, because there might be a special case, right? So you have to use one of the in-between words. And so, like, try to think about some examples of qualifiers. I can think of a good one that's kind of relevant, right? Here's like a figure from the pandemic, right? COVID, people were like, COVID vaccines are generally effective. And so that's a true statement about the vaccines back at the start of the pandemic, right? Because, like, even if you got the vaccine, some people, they had a bad reaction, or they still ended up getting a bad version of COVID. But most people, after they got the vaccine, if they got COVID, it was a lesser version of the virus. Right? So it's better. It's generally effective, right? So, like, that's like when you have to have, like, you can think of a number about it. Like, I'm sure it was bigger than 80%, but, like, if you think of, like, something is 80% true, then you can start using words on, like, this end of the spectrum, right? It's like, it's mostly true. It's getting a B, right? It's generally true. Something like that, all right? So those are the kinds of words we have to use to make sure that we're not, like, saying something wrong, all right? And so those are qualifiers, and we would like to be able to say something with, like, a qualifier in math, right? Because we remember that English sucks. English is very, very easy to get wrong and very ambiguous. It'd be nice to translate something like this sentence somehow into math so that everybody knows exactly what I mean. Does that make sense? There's a way to do that, actually. So that's pretty cool. Enter from qualifiers. Let's go to what's called a quantifier. All right. This is a bit of a harder topic. I'll go slow, but this is now part of logic. We're going to try and translate our qualified sentences to logic. All right. So remember that we've been able to do this for simpler sentences, right? We know about and, now, and or, and not, and we can translate English to those kinds of symbols to make things less ambiguous, which is nice. So yeah, we're gonna have some more of these symbols now. Let's go to math once again. So it's math time. All right. So here, this is kind of the goal. How can I translate my qualified sentences from English, which is ambiguous, into math, so that everybody knows what I mean, first of all, and then also in math we can prove things to be true. We can prove beyond a shadow of a doubt, and everybody agrees with you. So that's where we're going. All right. It'll take a little bit to get there, but I need to introduce two weird-looking symbols now. All right. Don't worry if you've never seen them before. These are called quantifiers. All right. These are two quantifiers. These guys. These two things are called quantifiers, and most of the qualifiers that we have in English we can use. We can represent using some combination of these two guys. For all and there exists. All right. Plus, like, our ands and ors and nots and things. So, plus these guys. Can't forget about those. Adding these gives us a lot of power to talk about qualified things. And so this first one, it's an A that's did like a flip. It's doing a 180. That's called for all. You read this symbol as for all. Okay. So it's like on this end of the spectrum. If you use the for all, it's like all, for sure, all. That's that one. And then this one, this is an E that's done a flip. It's like take an E and do a 180 again on that one. That one stands for there exists. So A and E essentially. For all and there exists. All right. So that one's a little more gray and muddy, right? It's kind of talking about the word some, kind of, isn't it? So that's helpful, right? So for all there exists. That's what those are true. That's what those are saying. And I'll talk about, like, how to fully interpret them in just a second. But there exist some other quantifiers as well. This is not the end of the story. And there are quantifiers in math that talk about, like, time, like something's not true right now, but it might be true tomorrow, like the future, right? But those are like graduate level logic class things, and work on getting your bachelor's degree first, I would say. All right, so you'll get there one day if you want to. So it's cool. You'll also learn about those in computer science. It's called temporal logic, which is cool to think about. But let's just work with these guys. For all in there exists. If you like what you hear, by the way, if you like this idea, proven things about just ideas in math, either become a math major or take CSCI 26. That will eventually teach you these once and for all, and you'll get good at them next year. So let me give you an example of taking an English sentence and translating it to using these quantifiers and then the other pieces of logic that we know about. Okay, let's give that a try. So here's an example of for all, using for all. So here's a sentence that I can translate into a use of this for all symbol, this for all quantifier, right? So, all right, this is trying to say, I'd like to claim in math that every value of some variable called x is greater than 5, right? I'd like to represent that in logic now. So here's the goal, all right? So we want to be able to, we want to write something in logic involving a quantifier that, will prove once and for all, right? If x is 7, the thing that I write is true, right? Because it's bigger than 5. If x was, it'll show that x can't be 2, right? It can't be 2 because that's not greater than 5. We want something that's true when x is 7 and false when x is 2, and every other number in between corresponds. All right. So here's how you translate this. Every value of x is greater than 5. So here's how you say it. I'm going to say for all values of x, for all x's, x is greater than 5. And so I've used logical symbols now, right? This is also a logical symbol technically. And this is the mathematical translation of that sentence. And if you're a mathematician or a computer scientist, you can understand what that means, and you understand that it means exactly this. Okay? Do you kind of see it? For all x's, x is greater than 5. That's how you can write, and it's unambiguous, right? And mean that thing. All right, so that's for all. Let's do an example of there exists now. So, all right, here's a sentence that we'd like to write in math. There exists a number called n that is both prime and even. All right, so again, this time when we want this sentence to be true when n is 2, right? N can be 2, that works out, but it doesn't work when n is 7, right? So it's the flip of that other one, kind of. Here's how you translate this into logic. There exists, you write that symbol, there exists a number n, and let's just say that let's just write prime and even so that we don't have to get into that. There exists a number n such that n is prime and n is even. Okay, and you can break down evenness and primeness into logical symbols and quantifiers later, but there's a way. Just take my word for it for now. But you see how I'm using that there exists. There exists an n such that this is true about n. N is prime and n is even. Do you see how that corresponds to the English? It's a little weird once you first see it. Don't worry, it'll take a while to sink in, but you can just come back to this slide. So those are the two symbols, and that's how you do the translation. Okay, so what I would like you to do and start thinking about quantifiers, we'll translate this to quantifiers in a second. I'd like you guys to please get into little peer instruction groups, say hi to the people next to you, and I'll stop attendance after we do this. Please go to the Written Ice page as a group and elect a leader, and here is your job. I'd like you to just use English right now. Don't use quantifiers just yet. Don't try to use those or anything. But try to specify what it means for something to be sorted. Like an alien landed on Earth and it didn't know what numbers are, or it did know what numbers are, but it didn't know what sortedness was. What would you say to convince somebody, to define to a child or something, that this is what it means for numbers to be sorted? How do you define that word? How do you define it in English with as much precision as possible? All right. So pretend that you're talking to a child or an alien who's never heard the word sorted before, and then we'll translate your ideas to quantifiers. So here is a list in Python. You can say that L is sorted, right? But why? What does it mean? What does it mean for a list to be sorted? You tell me. Right? Try to write as precise English as possible on the Written Ice page. Tell me what it means to be sorted. Okay? Now work together. And then we have questions about the question. What does it mean? Just in English. As many sentences as you can. Define sorted. What does it mean? Think about how quantifiers. Is that enough time? I'll give you guys another minute or so to get your answers in and press submit. What does it mean to be sorted? Very philosophical question, right? So let's see what kind of precision we figured out. How precise we got it. It's hard. It's not an easy question, that's for sure. All right, that was my timer. Very nice. Thank you. Thank you for submitting. Nice. We're on numbers 64 and 65. Let's see here. So a list of numbers that we use, and the order is chosen based off of rules and objectives that we are trying to achieve. That is technically correct. It's a little vague, though, I would say. A little vague because it doesn't really talk about, like, all right, why 8 then 27? Why not? Why does it have to be this order? Why couldn't the 27 have come first or something? So it could have been a little more precise. So what did group 65 say here? For something to be sorted, it means that there's some order that needs to be followed. From the given example, it involves stating that from the lowest number. Okay, yeah, now we're talking about lowest to highest. That's a little bit better. Nice. Lowest number, and every subsequent number afterwards is the next lowest. Good, good. Does that kind of make sense? That's like a little bit more precision, but yet, right, it's not mathy yet, is it? It's like kind of, let's see, let's talk about this. What does it mean that a list of numbers is sorted? So I think what you guys said essentially was like every number, like this is a list, every element of the list, right? Every element is like getting bigger or something, right? Does that make sense? Like that's how you could define sortedness, kind of, in English. We're just kind of saying something like this, like every element's getting bigger. Like 8 less than 27, 27 less than 42. All of those guys are hooked up like that, and it's like that, right? But actually, you could have had another list, right? This list, let's do L prime, is still sorted, right? 1, 2, 2, 2, 2, 3, 3, 4, 5. Why is this one sorted? Not the same, right? It's not getting bigger. What else do we have to say? Getting bigger or staying the same, yeah, or equal to. So it doesn't have to be true that your list looks like that. It could be this kind of like stair-stepping thing. It could stay at that number for a while. It's fine. But as long as it's getting no smaller, you see that? So it's really less than or equal to, less than or equal to, less than or equal to, less than or equal to. So that's kind of how you, like, that's a start of how you can start defining like what it means. Does that kind of make sense? And so, okay, we want to try to translate this idea to math. Let's figure it out, all right? I think, because, like, let's go into, let's use our Python knowledge, right? This is a list. Let's pretend like somebody gave us a list in Python. How can I prove that this Python list is sorted? Well, I can do this kind of process. Like I can say that 8's less than or equal to 27, 27 is less than or equal to 42. And this could be just some arbitrary list. So like you can say this, you can use the indices, can't you? Like this is index 0, index 1, whatever these numbers are, index 2, index 3, index 4. Whatever these numbers are, like if this list L is sorted, L of 0 better be less than or equal to L of 1. Does that make sense? L of 1 better be less than L of 2. Yeah? And so on and so forth, up until you get L of 3 less than or equal to L of 4. If you have all of those at once, then your list is sorted. Yes? That's the secret. All right? So in general, you could kind of like, you could say this, right? L of some variable I is less than or equal to always, like, go to any index I. There's a for all kind of in that sentence that I just said, isn't there? Go to any index and check the thing right next to it. I plus 1. Is this true about those two things right next to each other? For every I, see that? That's going to be the trick. That's how you can specify it. And like that, you can, all right, you get this one out of the deal when you set I to 0, right? That'll compare index 0 to index 1. And like when I is 1, that will give you this calculation. Yeah? If you just do a bunch of these with the correct values of I, you could say it's sorted. Any questions about that before I translate it to math? So kind of in general, try every possible I value that works for this list. Like don't go and make it 5 or something. Don't make it be bigger than it needs to be. Don't try to go past the list. But for every valid value of I, like do this and make them all true. Make sure they're all true. If they're all true, then it's sorted. Because they're all less than or equal to, you get the stair-stepping effect. Okay? So, drum roll, here is the answer. Here's kind of how you would say this using quantifiers. So for every I, kind of implicitly, that makes sense for this, whatever list you've got in front of you, check L of I, your current index, and the one right after it, and you're going to try them all, right? Check each pair of indices, essentially, and make sure that the thing right after is bigger than the thing, or equal to the thing that came before. Like check these guys. Check those guys, oops. Check this pair, I is a 2, right? I is 3, and then you're done, right? If it's all true for all I's that work for the list, then you've got a sorted list. Are there any questions about how I'm reading that or how I created that idea? It is the symbol is weird, the idea is weird, I'll give you that. It does take a while to sink in, so just let me know if I can help with anything. but kind of here's how you read it. For all i's, like for every index I that like works for the list, if you go to L's element at index I and you compare it to L's element at index I plus 1, so the one right after, make sure that it's less than or equal to in that order. And that will try, right? You'll try that pair, that pair, that pair, and that pair, and you'll get all the things that you need to mean that it's sorted, right? Until the list is over. Isn't that cool? Yes?
Before you showed us this was online, it was like a visual of how the computer does that. What was that called?
Let's see. I think it might have been Python tutor, like C++ tutor is what it was called. There's one for Python. Did I show you guys that one? Can't remember. Nice. Yeah, so that exists for Python too. It's really cool. You can step through your code. And this is like, if only we could do that for math, essentially. If only we could do that for math. That would be cool. That's what we want. That's what we want. That kind of stair-stepping through, trying all the possibilities. Kind of like a loop in math, essentially. That's what a for all is doing. And we will talk about that correspondence very soon. All right? So that's a good question. Any other questions? Because I want you to try now something. Here's another idea. All right? Here's what we came up with. Here's our answer from last time. Here's the for all quantifier. Here's a there exists quantifier. Remember that one exists as well. So I'd like you guys to get back into groups. If you have your thing open, you can just re-click submit and change it. That's fine. So I'll keep these up. I won't delete them if you still have it open. It's not a big deal. But I'd like you this time as a group to try to create a statement this time. You're going to go from English to math if you can. Try to say this. Okay? So like here's the English. I want you to go from this to math. All right? Use quantifiers to represent the idea that this is true. Every non-empty list of numbers has a minimum in it somewhere. That's a true statement, right? If I give you a list of numbers, there's a minimum somewhere in that list. How would you specify it, though? How would you translate that to math? How would you say what minimum means in logic? All right, so like every non-empty list, so like the list with just 1 in it, it's got a minimum. It's that one element 1. The list 3, 1, 2 doesn't have to be any ordered thing, but like there's your minimum. It's somewhere in the list. Every non-empty list of numbers has a minimum. The empty list, there is no minimum because there's no elements. And every other one, right? There's a minimum somewhere. Does the question make sense? See if you can try it. Don't worry if you're feeling shy. You don't have to post it, but like if you can, try. Just like spell out for all, spell out there exists. But see if you can do the translation. Talk about how you might think of it or approach it as a group, and then we'll come back in a few minutes and see if anybody figured it out. What does it mean? You have to again figure out what does it mean for something to be a minimum this time. What does that mean in math? This is a harder question. a few more seconds to discuss. It's okay if you don't have time to type it. I just want to hear your thoughts. All right, what do we think? What are our thoughts? What does it mean? First of all, what does it mean that there's a minimum in a list of numbers? Like, how do you define minimum? Like, that's a sub problem, isn't it? Do we actually type stuff? So, very cool. Nice. For all L that exists, Li that's less than or equal to all other nice. Very nice. That's kind of the idea. What's that? Say that again. Yeah, so I'll show you that. That's really cool. Yeah, it's going to need another for all. Yeah, I'll show you. It's really cool to think. So yeah, what do you guys think? Anything similar to that or something unique? Oh, like make it sorted? Oh, nice. I like that. I like that a lot. That's definitely another way to look at the problem. Because like sortedness implies, like once a list is sorted, that implies like you got that chain of less than or equal to's, and then you know like everything is less than or equal to this one at the start. That's very good. Yeah, I hadn't even thought of that. That's a cool one too. Yeah, let's see. Let's just assume that the list is unordered, and let's try to write something general. Okay. So yeah, I liked your guys' thought. Like this is great thoughts. I'm glad we had this question today. Very, very good work, you guys. Let's see. I want to be here. All right, let me show you. So first of all, some words you can immediately in this quoted sentence can be immediately translated right to the quantifiers. There's every, and then there's has a. You see how every is gonna mean like you're gonna have to add at least one for all in this answer, right? Has a is like pretty much a synonym for there exists. There is a right minimum. There exists a minimum. So all right, let's talk about this. How do we translate it? All right. So first of all, every non-empty list of numbers has a minimum. We have to like talk about like the list. We have to like say what list we're talking about. Like this one, like there was a list L. I gave you a list L. Like for this one, it's talking about every single list under the sun. Like for every list, every non-empty list. We have to give that a name. All right. So a lot of times we have to introduce brand new variables, and that's actually what quantifiers do. When you use a quantifier, if you notice, like in all my examples, there's a variable right after the quantifiers. It's creating a brand new math variable whenever you use a quantifier, essentially. Right? So we have to introduce a brand new variable for an arbitrary list of numbers that has a name now. We can use that name later. All right, so here's kind of the first part of it. Here's this, or we're going from this to a bit more precise English. So for all lists, call them L. Right? If L is not empty, then there exists a minimum value in L. You kind of see the steps to get from there to there. It's still the same. So you got your for all now. You got it there exists, so it's going to be translated. And then I also did something else, right? Every non-empty list of numbers had a minimum. Like that's a quick English way of saying this, right? If L is not empty, then there exists a minimum value in it. And we know that if-then statements can be translated to an implication in logical symbols. So like that's getting better. That's getting to where we need it to be, right? And then we just have to think about minimums next, right? What does it mean for there to be a minimum in a list? We have to like talk about like what mathematical symbols can we use? Probably more quantifiers. What does it mean that there's a number and it's called the minimum? Right? We have to describe it. Describe it using its properties relative to other things, right? So like what does it mean that a number is the minimum of a whole bunch of numbers? it's the smallest, right? It's the smallest. Or if there's duplicates, it's like it's less than or equal to every other number in the list. That's what it means to be a minimum, yes. There is another quantifier. So secretly, the answer is going to be involving two for alls. One for the talking about the list, and one for like talking about every other number in the list. See that? Slowly but surely, we're getting there. And so yeah, we have to like introduce more variables. Let's go back to like let's use this idea of indices. I think that would be the easiest because I already gave that example. So let's talk about indices, where those numbers exist, like where the minimum lives, where every other number exists. All right, so we'll add some more variables to talk about like the minimums index, like we'll quantify over that, we'll say. And like we'll talk about the indices of all the other numbers, where they live. So here is going to be the answer, all right? Well, I still need this, right? For all lists L, for all L. For all lists L, if L isn't empty, then this is true about L. So if L isn't empty, how would you talk about that in math? Like, all right, we can use Python, I guess. We'd be like, all right, if L isn't empty, then if the length of L, right, is greater than 0. That's true when it's non-empty, right? If that's true, then do the other part. So that's the if L is an empty part. Does that make sense? Say that again? Yes, we would totally do that if we were doing real math right now, but I don't want to teach that symbol too. Yeah, so you're right. You're exactly right. So like pseudo Python-y math, this still works, right? If the length of the list is greater than 0, that means it's not empty. If that's true, then now we need to translate this part. There exists a minimum value in L, all right? And so now here's what this means. Let's do it. So I need something very long to mean there exists a minimum value in L, all right? So let's talk about it involving its index. Let's say like not just there exists a minimum, there exists a place where that minimum lives. There exists a minimum index. We'll call it min idx. All right. So again, I'm creating a variable. So for all lists L, if L is non-empty, the length is greater than 0, then what's true about it? There exists a minimum index such that compared with every other number in the list. So if you go to all other indices, including that one, call them I, then what's true, looking at L at that min index where the minimum lives, the value is always less than or equal to the value at your other index I. And I is going to range over everybody. Do you see that? It's very, very weird. It is a little involved. I know, it is hard. But that is going to be the answer if you go this route and you use indices. So for all L, if the length of L is greater than 0, it's not empty, then there exists a minimum index such that for every other index, including that one even, L at that index, right, and we're trying all I values, 0, 1, 2, L at the minimum index is always smaller than every other number in the list. Okay? That's how you read it. It's quantifying over every other number in the list right there with that other for all. That's the secret, and again, here's how you would like translate it to English. Translate it back to English. Very precise math. It's like, all right, for all lists, call them L. That's the first part, right? That's that part. If L's length is greater than 0, that's that part. Then, all this, right? Then there's an index in L called min index, such that for every index I in L, try them all, this is true about each index I. Right? So it's ranging over all of them. It's doing like a loop over every index in the list. All right? So that is the long-winded answer. And that is super precise. So now we could, like, everybody will agree, all the mathematicians will agree, like, that's correct. You can go off and prove that that's true, and everybody will believe you. All right? I haven't told you how to prove it, but that's how you can state the idea. Okay? Any questions about that? It's a weird little concept, I know. So if you like this stuff, consider becoming a math major or stay in computer science and take CSCI 26. All right, so yeah, that's where I want to stop for the day. It's enough to talk about, I think. We'll come back and talk about quantifiers a little bit more later, but what I'd like to do now is release your next programming assignment. Even though this wasn't a programming lecture, it's normally due on like a Thursday, right? So I might as well give you one now. Here's your next programming assignment. All right, so it's going to be very similar to some code that I did in class, right? I did like 50 random squares, right, of random colors. So here's what I want you to do. I'd like you to make a bunch of random squares and triangles, okay? A program that does that. So write a Python program that uses turtle and random to do the following. What I'd like you to do is ask the user to say how many things they want drawn, how many shapes total they want. So you got to ask them up front with the input command, the input function. It's like they'll type 50, then you'll draw 50 random squares and triangles. All right. If they type 100, then you'll draw 100 random shapes. Okay. So you're asking the user up front for a number, and then you're going to loop n times, right? One for each shape that you want to draw, and do the following. All right. So you'll set the color to a random color. I showed you how to do that, right? Here's a page that has every color name that Python cares about. You can set the fill color to pale violet red if you wanted to. Okay, so you can make a big long list of these if you'd like. Those are all the colors Python knows about, Turtle knows about. And then, all right, you got your random color. Then next, for this particular shape, you have to flip a coin now to figure out, am I going to draw a square right now, or am I going to draw a triangle right now? Does that make sense? Because you want to be able to draw both of these, squares and triangles, and a random amount of each, totaling up to n, whatever the user gave you. So now flip a coin. So get a random number. If it's like 1, draw a square. If it's 2, draw a triangle. Something like that. All right. So pick whether to draw a square or a triangle. And so when your program runs, it should draw not just like the user types 50. Don't just draw 50 squares and 50 triangles. You're drawing 50 shapes total. All right. You're flipping a coin each round. Okay. For shape number 10, I'm about to draw. Okay, it's heads. I'm going to draw a triangle. Or if it's tails, I'm going to draw a square. Does that make sense? Yes. If you want to do like random.choice and you looked into the documentation, yeah, that's totally fine. You could choose a string. That would work for sure. But yeah, I think the easiest way to pick this, like to do a coin flip, would be to choose a random number between 1 and 2 and then have an if statement. If it was 1, then I'm going to draw a square right now, randomly. Or if it was 2, I'm going to draw a triangle in a random spot. Okay. So that's going to be the idea. You're drawing some squares and some triangles. In total, you're flipping a coin each round. The total number of shapes is the number the user gave you at the start. All right? So random. After you've picked what kind of shape, then pick a size for it, right? Pick a random size and a location, and like go to that random location, that random size, and draw the square or triangle, depending on which one you just picked. Okay? With your random color that you chose up above. Does that make sense? So n shapes total. Like if the user asks you to draw 10 shapes, maybe the first round you'll randomly pick to draw a square. You'll go to a random spot, draw a square of a random size, and then maybe the next round, round 2, you'll pick to draw a triangle. Like it's random. Each time you're flipping a coin. Maybe it's like first a square, then 2 triangles, then 3 squares. I don't know. As long as it adds up to 10. Okay? So that's the English description. Does that make sense? All right. So this is just me forcing you to use randomness and loops, right? You're looping a certain number of times. You don't know up front how many times the user wants, so you're looping. And then you got to use an if statement, right, after you do some random numbers to say, all right, I'm going to draw a square right now, or I'm going to draw a triangle right now. So it's just a bunch of practice with stuff that we've done. And yeah, so you should be able to use a lot of my code from last time with that random, drawing like 50 random squares, right? Just change it to not draw 50, but like n random squares, and then like bring triangles into the mix. It shouldn't be too horrible, okay? And remember that you're drawing n shapes total. In each round, you got to flip a coin. Am I going to draw a triangle right now, or am I going to draw a square? Okay? So yeah, what I want as usual is a video of your program running. Show me your cool stuff. Walk me through your code. And yeah, it doesn't have to be long. I think that's all that I wanted to say. And this will be due a while from now. So week 14, we got plenty of time to work on this. I think there's still one that's not even due yet, right? Like this one. So you can work on both of them at once if you'd like. So you got 2 programming assignments out right now, but you got plenty of time to do each. Okay? Are there any questions about this assignment? So yeah, I'm excited to see the pretty pictures that your programs draw, and I think that is all that I wanted to say and record today.